Welcome to the lecture series on mathematical modeling, analysis and application. In the last lectures, we have discussed about this population balance modeling and its solution process. And in that level, we have discussed like how this population level will grows like in an exponential way, or it can just achieve the steady state, or how a nonlinearization technique can be used to linearize the factors, that we have discussed. And in the final phase we have concluded as how this physical behavior is matching with this mathematical representation of this modeling. And in this lecture we will discuss about continuous time single spaces models, and these models will include for single spaces populations. And then we will just develop this model, and based on that we will just test like the growth rate of function, how it is just affecting the population rate, and final form we will just discuss about early effect model. So, if you will just see this models for single spaces model, till now we have discussed like exponential growth, logistic growth models, both for discrete time and continuous levels. So, the models are described either in the exponential growth model, as I have told, that is basically called Malthus model, and this model especially in mathematical representation it was written as like dn by dt, that is nothing but k into n we have just written. That is, whenever there is a change of this population growth rate or decay rate, that depends on this rate of population change, especially k, and that we have just represent as in the form of r here. And the solution of this model, that is just given you the exponential model. If you just see, we have just written there as n of t as e to the power kt into n0, where n0 is nothing but the initial population size we have just considered, that is at t equals to 0 we will have like n equals to n0, and that is especially called Malthus model. But the Malthus model was not valid always, since there are many restrictions available, or it can just exist that the population will not always grow in an exponential way, or it will not decay in an exponential way. Since whenever we will just consider this growth rate, we have to consider birth rate, death rate, and all other physical aspects or the physical behavior of the system at that time. Maybe you can just visualize that if there is a population of like tigers or deers, it is just existing in the atmosphere, where tigers are like eating deers and deers are just fed by the grass. So, in that level sometimes you can just find that if there are some natural devastation or some cyclones are coming or some other aspects they are coming, then both the deers can die or these tigers can die. So, in that level this model cannot be valid, since we are just assuming that only these tigers will eat these deers and deers will eat the grass and the population will grow up. But always that is not possible. Maybe some like disease will eradicate that, this can just this growth rate can be broken down. So, up to like certain level we can just assume that this Malthus model can be valid, but after that we cannot assume. That is why this logistic growth model comes to the picture, and this logistic model especially it is called Warhol's model, where we have just assumed that this k, which is just assumed as a factor of like k into C0 minus alpha n of t. This alpha n of t, if you just see, that is nothing but the restriction factors, that is just objecting this growth rate of this population size, and especially many factors can be come to the picture here. And if you just see here, first one is a linear model here and second one is a nonlinear model. Since if you just multiply these factors, so first term it will just give you a linear term here, but the second term it will just give you a second order term here. And especially we have just find the solution for this differential equation n dash t, and this solution is represented as n of t equals to a n0 by n0 plus a minus n0 e to the power minus gamma t, where the parameters like a is defined as a c0 by alpha and gamma is defined as kc0, where this population at 0th level or t equals to 0, the total population size is assumed to be n0. And if you will just go for like models for single species population, that is extended to our earlier case, if we generalize these two models, then it can be written as like n dash t equals to f of n. So, always we will have a function f of n, which may be linear function, which may be a non-linear function. And especially if you just see f n is a linear function for exponential growth model and a quadratic equation for logistic growth model. So, in general we can write f n as a polynomial of some finite degree. So, how we can just linearize these functions, that we will just consider here. So, if you will just recall our earlier lecture, then you can just find that we linearize a nonlinear function by Taylor series method using certain functions. There is a like a perturbation of the values we have just assumed like capital X and italic X, and then we have just to find this Jacobian, and in that sense we have just to find it in a matrix form and we have just linearized this system. Thus, we obtained an equation of two infinite terms. So, if you will just assume like finite number of terms, then we will have a polynomial, and if you will have like a infinite terms, then we will have a series solution. Hence, f of n we are just representing as summation n equals to 0 to infinity a n n to the power n. So, either way you can just represent that one. So, if it has like finite number of terms, you can just say it is a polynomial. If it is a infinite number of terms, then this is like a series expansion, that is Taylor series expansion you can just find. In the Taylor series also we are just finding that this is expanded up to like certain number of terms, and after that we are just assuming the term as the remainder term or the error term. So, if you will just go for like models for single species population here, then one axiom, it is called axiom of parenthood, it is assumed. This axiom is given by Husson, which says that every organism must have parents. If parents are existing, then you can just find the growth of population, or like their child will exist there. If there is no parents, then there is no population. So, that is the basic idea of this axiom of parenthood. Think for any animal which you can see in your neighborhood often. If they have the parents, they are existing, and if there are no parents, then there is no existence of this animals. So, this is the case like dinosaurs, you can just say, we are just saying that dinosaurs are existing in the world, but now we are not finding any dinosaurs since they do not have any parents, or they do not have any like parent. So, this axiom is equivalent to 0 growth rate for 0 population, that is n dash t equals to 0 at n equals to 0. Obviously, if you will just assume n equals to 0, then you can just find like a dn by dt, this is 0. But otherwise we can just if you will assume, if you will just find the solution, whatever the constant we will just get from this n of t equals to constant, this constant is nothing but c equals to 0 there. So, in general model, if you will just assume suppose n dash t equals to f of n here, and after applying axiom of parenthood, the condition is equivalent to f of 0 equals to 0 here. Since if you will just assume like f of 0 equals to 0 means the population size is 0 suppose, then dn by dt this is also 0, and obviously in reverse wise if you will just consider this integration n equals to constant. So, obviously we can just say c equals to 0 if there is no population. And in that sense we can just say that if you just take the expansion of this series here. So, first term is a0 into 0, sorry, this n to the power n means n to the power 0 here, 1 there. So, that is why we can just assume a0 equals to 0 here, and from this equation 16.3 obviously we can just say that f of 0 especially this is written as a0 into 0. So, that is why A0 is assumed as 0 for this equation. So, no offspring can come out if there are no individuals. If the population will exist, then we can just start growth of the population, it can just grow up, but if there is no population, then it cannot be grows it up. So, that is why this axiom of parenthood can be applicable in this model. And in a generalized sense, if you will just write this function, that is n dash t equals to f of n, and f of n is written in the form of summation n equals to 0 to infinity, and a n n to the power n, then we can just write this one as like n dash t as f of n there, and which can be expressed as n equals to 0 to infinity a n n to the power n there. So, then we can find here the expansion as a 0 plus a 1 n a 2 n square plus of 2, the nth term it will be like a n n to the power n plus all other factors. So, if you will just see here a 0 equals to 0. So, that is why this equation is written in this form here, a 1 n, a 2 n square, or a 3 n cube. So, this can be written, and if you will take common of this n factor here, so this can be written as like n into g n, where g n can be expressed as like a 1 plus a 2 n plus a 3 n square. So, likewise we can just write this is a increasing like intrinsic growth rate function. So, if we will just examine this growth models on the basis of intrinsic growth rate function, then we can just find that the Malthus model will give you like f n equals to r n here. So, obviously we have just write that one as the exponentially growth population level. So, in this case we can just write g n equals to r there, that is a constant line with respect to n. So, if you just put in a graphical sense, this is the constant line we are just putting g n equals to r. Now, we can just say that this population level will growth, or the population level will grow exponentially, but this increment rate it is fixed. So, that is why we can just say that what is the biological meaning associated with this. Mathematically it describes that for any number of population the intrinsic growth rate is same. This means that there is no competition at all and sufficient amount of resources are available at time for their survival. This means that maybe 5 population, if it is 5 cells are there, sufficient food it is available, but the increasing rate is like 5 suppose, and even if the population size is suppose 100, the intrinsic growth rate is like 5 then 1000, the intrinsic growth rate it is also 5 there. So, then it does not hamper that whether this like resource is deficient to them, or it due to scarcity of this resources, the population growth rate it will hampered. So, always you can just find that this intrinsic growth rate it will be developed without this dependency of this resources there. So, if you just consider this Verholt model or this nonlinear growth model, then we can just find that this function f of n is expressed as k n of t c 0 minus alpha n of t. So, g n, which can be written as here as, since n is present here, so k into c 0 minus alpha n t, that is a straight line with negative slope with respect to n here. If you will just differentiate this one, then we can just find that this line, that is if you will just differentiate here g dash of n, that will just give you minus alpha k here, minus alpha k. So, then we can just have a like negative slope with respect to this number of population size, and this figure this shows that the intrinsic growth rate is monotonically decreasing with respect to n here, and this means that the size of the population increases, the growth rate decreases because of increase in the competition of resources. So, if the population level will be higher, then they will like consume maximum amount of like resources available there, and then this population will compete each other to get the food, and the population level will decrease. So, that is the basic idea for this nonlinear model here. So, even if this intrinsic growth rate is monotonically decreasing to n, but the size of this population, it will just get increased, but the resources it will just get like a decreases. So, this means that the size of the population increases, the growth rate decreases because of increase in the computation of resources. Since the same food it will be provided to all this like cells or this like animals, it is just present. So, then they can just compete each other to like increase their growth rate, but definitely you can just find that this growth rate will decrease. So, that is why if you are just plotting here g of n, that is the total population growth rate. So, it is just representing the declination of this one with respect to the total number of population. So, next we will just go for a Ali effect here. So, this means that if you just consider Gn as a quadratic equation, suppose where we are just assuming a2 is greater than 0 and a3 is less than 0, then one can obtain this Ali effect model. So, this is the restrictions it should be provided for this quadratic equation, then we can just say that it is a Ali effect. And the classical view of this population dynamics states that population will experience a reduced growth rate for high density of individuals and a high growth rate for less density. So, this means that the population will experience a reduced growth rate for high density of individuals. If lots of gathering is present at a position, definitely they will just compete for all of these resources there, and high growth rate, less density means logistic growth we can just find. But the American ecologist this Ali, he observed that this reverse phenomena is observed in case of a goldfish. If like the growth is found to be like very fast when there are more individuals are present in a tank. So, that is why it is called Ali effect, and this is a special case which has been developed by this Oder Clade Ali. So, that is why it is called Ali effect. So, if you will just consider like different cases in different forms, then we will have like different classical models in population dynamics. So, if you will just go for the solution of this Ali effect equation, that equation is represented in the form of like change of this population is directly proportional to the total number of population size into this growth rate factor into n by a minus 1 into 1 minus n by k. Especially here we are just assuming that k is the maximum carrying capacity, or it is just said to be the critical value here, and a is the critical point we have just assumed. And the steady states are like, if you just see here dn by dt equals to 0, obviously we can just write n equals to 0 or n equals to a or n equals to k here. And the nature of this graph, if you just see here, so Gn is nothing but here which can be written as like r into n by a minus 1 into 1 minus n by k. So, if you just plot this graph of Gn here, that is in the form of r into n by a minus 1 into 1 minus n by k here, this will just represent a parabola which is just opening downward here. And this means that the first increasing growth rate will increase here. This is the increasing phenomena we are just getting, that is as the number of individuals increases, and this rate will decline due to the competitions started here. From here onwards there is a decline of this nature. So, this is the general idea about the Ali effect, and if you just go for this solution of this Ali effect model, then we will use this variation of separation or a variable separation method to get the solution. So, if you will just see this equation here dn by dt, and if you want to free n from this right hand side, and if we want to keep only this constants and dt terms in the right hand side, we will just keep this equation in the form of like 1 by n into n by a minus 1 into 1 by n by k into dn, this equals to r into dt plus a constant. And since these are all nonlinear terms, So, we can just factorize this one in the form of like 1 by n into n by a minus 1 into 1 by minus n by k, which can be written as, since 3 n factors are there. So, that is why we can just write C 1 by n here plus C 2 by n by a minus 1 plus C 3 by 1 by n minus k here. And if you will just compare both the sides, then we can just find this C 1, C 2 and C 3. So, if you will just compare here, this means that this denominator part, it will remain same. So, first C 1 into n by a minus 1 into 1 minus n by k, this is just considered as a plus C 2 can be considered as C 2 into n into 1 minus n by k plus C 3 into, we can just write as n into n by a minus 1, this equals to 1. And if you will just compare all the powers of n, then we can just find C 1 as minus 1, C 2 as k by a into k minus a, and C 3 as k by a by k into k minus a. After this expression, so once you are just getting these values of C 1, C 2 and C 3, then we can just integrate and we can obtain the values of n of t. And if you will just go for this solution of Ali effect in a graphical sense, the nature of n of t is shown as that for some particular value of k, that is a maximum level of a population, it can be maintained when t tends to infinity. This can be assumed to be a constant level we are just finding here. And if you observe the graph for stability, then you can just conclude that any arbitrary point chosen near the steady state n equals to a will converge towards the point a here, and the same for steady state n equals to k also. And the steady state n equals to 0 is not stable, since if n equals to 0, then there is no growth rate or no decay rate, since population levels should be present there. So, in this lecture we have discussed about single species population model, then intrinsic growth rate function and its significance. And in the exponential growth rate, we have just find that this intrinsic growth rate function, that is independent of the resources available there. This means that sufficient resources, it will be available there, and this intrinsic growth rate, it will not get changed even if this population size is 5 or 100 or like 1000, it does not affect it. But if we are just assuming like nonlinear model, in that case we have just observed that this population size, they are just competing each other, and this population level is just getting declined. And in the last phase we have just discussed about this Ali effect, which is effective in case of certain population levels, that is goldfish, as it is just found that if the certain individual numbers, maximum amount of numbers are gathered in a place, then we are just finding this population level is just getting increased. And then we have just find the solution of Ali effect model. So, thank you for listening this lecture.